And it looks like we are on. Good evening, everybody. Welcome, good morning, I should say. Good evening if you're in the United States. Good evening to my colleagues and friends over in Europe. Thank you for getting up at 2, 3, or 4 o'clock in the morning. You didn't have to, because this video is going to be available as soon as it's over in an hour. But some of you said you were getting up, so thank you. I'm honored to be here. And to my colleagues and friends in Australia, hope you're having a great midday, lunchtime about now. But my name is Tim Brzezinski, and here I'm going to demonstrate how you middle school and high school math teachers can use GeoGebra Augmented Reality as a powerful tool to engage students in modeling their 3D world. It is an amazing app, and it brings to the table what has never been able to be done before in mathematics education, right? Now, I don't think any math teacher here in the US or around the world would really argue that and say that, well, modeling mathematically is not really important. We all agree that students need to be able to model, their real world with mathematics, right? And we don't live in a 2D world, two-dimensional world. We live in a three-dimensional world. Now, GeoGebra Augmented Reality helps students build 3D models of real-world objects or even create 3D mathematical art, right? It's a science and an art simultaneously, okay? And from that, students can make not only rich discoveries, but have so many aha moments that with simple concepts that often teachers, especially in middle school, high school geometry, have struggled to have students just get, okay? But let's struggle no more, and let's actually get started. So what I'm going to ask you to do is to take out your iPhone, your iPad perhaps, or I'm going to actually classify devices into two different types before I screen share. There's the iOS, which is, Apple pretty much, iPhone, iPad. And then I'm going to categorize the other branch as the opposite of iOS, which is non-iOS, okay? And again, not necessarily Android, but Androids fall in that category. I'm talking Androids, Samsung tablets, you name it, okay? So let's screen share here and get started. So there we go. And fractal. All right, so now let's get out of here. So here's what we're going to do to get started. All right. If you have an iOS device, iPad or iPhone, that is, okay, what you need to do is go to App Store now and download, or just type in under search, type in GeoGebra Augmented Reality. Okay, and it'll pop up there. It should pop up. It's this little, it's this pyramid with the letters AR in the right corner there. And I believe with that, you need, you can't have an iPad or iPhone that's too old. And I think you also need something like iOS, like operating system 11 point something or higher, I believe. I don't know the exact specifications, but your phone will tell you. Now, if you're one of those people that never actually update your settings, that could pose a problem at this time. So take a minute or two to update your settings if you need to, and you should have time to do so. All right. So people on iOS, that's going to be the toy we play with right there. All right. Now, if you have a non-iOS device, like I'm talking Androids, other devices, okay. Again, nothing with a keyboard. It has to be a phone or a tablet. Okay. For Androids or non-iOS devices, you're going to download two items. The first item is imperative, okay? You need to download GeoGebra's 3D graphing calculator. Right now, I got mine off of Google Play or Play Store, I'm not sure what you call it, but that's what it looks like right there. Now, and if you want to bring out about the augmented reality component within GeoGebra's 3D app here, you're going to have to install a second app on your device called AR Core by Google. Okay, so I'm going to make this a little bit smaller here so you can see it. And let me just change the view here to something like 75 so we can see it all. Again, if you have an iPhone, you have one app to download. That's GeoGebra Augmented Reality, AR right there. You'll find it in App Store really easily. If you have a non-iOS device, Android, others, whatever, you're going to download GeoGebra's 3D graphing calculator. And then if you want augmented reality within that 3D graphing calculator, you need this app called AR Core by Google. All right. So those are the necessary requirements. Now, in this screencast, I'm going to be using both devices. I'm going to be pretty much using Air Server app to just mirror my my iPad and also my Acer Chromebook Tablet 10. All right. Again, my heart's intent here is to come across as being device agnostic. Okay. Yes, I have a favorite platform, but that's not my place to share here. Okay. I want to show you the accessibility of GeoGebra Augmented Reality on all devices here. All right. I'm gonna actually start with the non-iOS first. Okay. So yeah. So while I actually set up here, I'm just gonna need to mirror something here. So just give me a second. Again, take your time to do that. This should take 10 or 15 seconds, not even. All right. Please feel free to leave questions in the chat. Okay. I have my friends and colleagues Mallory and Sarah here. They're actually reading the chat window because as I'm screen sharing, I cannot read the comments and questions that are coming in the chat window. But if you have questions or comments, please type them in there. All right, and I beg you to. And if they notice that there's a common question asked like a lot, they'll bring that to my attention so I can address it at that time. But when the screencast is totally over, I'll go through everything and watch it and then try to answer as many questions as I can in comments. All right. So whoops, let's see here. Just give me a minute. And we'll do this. Whoops. Oh, hang on. And cast. Okay, share. There we go. All right. So now let me. All right. So right here on the right side, I actually have my iPad. I didn't realize that was hooked up already. On the left side, I have my Acer Chromebook Tablet 10. But let me actually. Hang on a second. I apologize. I didn't intend to do that. Let me just stop that for a second. And let me go here. Technical difficulty. Hang on. I'm going to close that out. All right. And let's do this. All right. So I only want to be looking at the Acer Chromebook right now, not the iPad. We're going to look at that in a little bit. Now, I apologize for the quality here because I actually tried the app that I usually use to mirror my Chromebook is Chrome Remote Desktop. Anytime I do webinars or PD with math faculty all over, that app works really well. But for some reason, Murphy's Law, right? I have the screencast tonight, and Chrome Remote Desktop was just bugging out on me. So when I mirror this on AirServe, it doesn't look the greatest, but it's not Acer. It's not Acer's product. It's not GeoGebra. It's just simply the connection here, basically through AirServer. But that's okay. But as you can see, I'm going to keep it small. So right here, you'll notice I have GeoGebra's 3D graphing calculator. It's kind of small there, but the smaller I make it, the clearer it is. So I'm going to hit it. There you see GeoGebra. Okay. This is for non-iOS devices. So if you have your Android, we can come out and play here. Now, up here in the upper right corner, you'll see the settings icon right here. We're going to start in middle school right now. So you middle school geometry teachers, high school geometry teachers, so many teachers tell me, Tim, my kids struggle so much when I have to teach them, surfaces of revolution, like, when I rotate a line about another line, describing the surface that results. They also struggle teaching cross sections of two surfaces, right? But GeoGebra's 3D graphing calculator can actually help take that struggle away. In fact, it can not only do that, but have the kids tell you what you want them to discover instead of you telling them. And I'll show you what I mean. So if you go to the gear right up here, I'm going to do that and just go to general. It's on the very far left side. And I'm going to make my font size like Reader's Digest Senior Citizen big print style here. All right, so it's easy to see. And what I'm going to do here for input, I'm just going to type a function. The most basic of basic functions, right, is a linear function, as we know. And let's just simply type in, say, f of x equals, let's say, x. And now I'm going to restrict the domain. I'll put a comma there. I think maybe making this smaller might help you see it better. I don't know. I apologize for the pixelation here. But 0 less than equal to x less than equal to 4. Right? So you see, all we did is graph the line y equals x going from 0 to 4. We type in our function, put a comma, enter our domain restriction. And I'll hit enter, which is in the lower right-hand corner right here. All right, so there we go. There's the line. And actually, I'm going to hide this gray plane too, because I don't really need it. So if I click on the right settings gear up here, I can actually just turn off the plane. I can turn off the axes. I can do a lot of things, but I'll leave that there. All right. In fact, if I touch on the 3 dots right here, the 3 tiny small dots, I can actually change the color. I could, under settings, I could style it. I could do all sorts of things, but I'm just going to make it black right there, like such. Okay. So now our goal, now the x-axis is red, right? The y-axis is green. And all right, I know that certain middle school teachers, middle school students, I should say, kind of freak out. What's that third axis there? Well, that's the z-axis. Again, not too early to introduce that to, say, middle school students and even high school students. You don't need to wait till Calculus 3 multivariable to do so. But let's actually, and over here, many of us that use EdTech, free EdTech here, platforms, we like to make sliders. So I'm going to type in the letter N and enter. Now, N is a slider. It's hard to see with the pixelation here. And again, I apologize. But N is actually going from -5 to 5 right here. But if I click on the dots, if I click on the 3 dots right here, all right, I'm going to go to settings. And I'm going to make the minimum 0. And I'll type in DEG. I'm too lazy to find the degree symbol. But we're going to go from 0 degrees to 360, letter DEG. Okay, and I'll increment by, like, say, 0.01 to make a smooth increment. Because what that slider is going to do, all right, and when you finish, just touch out in the white here. Right, so what I'm going to do, now, GeoGebra converts to radians. I don't know if you can really see that well, but it says 6.28, which is the approximation for 2 pi. All right, but even for middle school, high school, so what? I mean, in my opinion, I think middle school students should be learning about radians. To me, it makes more sense to wrap a radius around a circle, right? Then it's more natural than it does to cut a circle up into 360 equal chunks, right? Like the ancient Babylonians did. But now here's where the magic happens. Check this out. Okay, go to input now. And then if you go over here where you see my mouse, if you touch those 3 dots there, I know it's hard to see on my screen, touch them. And where it says search all commands up top here, type in the word surface, SURFA, and it actually will just come up there. So if you touch the word surface, it'll populate the cell. So now I'm going to tell GeoGebra, here's what I want you to do. I want you to take this surface. I want you to create the surface. I'm going to go to ABC. I want you to take function F, comma, right? I want you to rotate it by angle N. Ooh, check that out. Comma, and then I have to indicate the line. And that line is the X axis. And I'll type it just like that. So again, GeoGebra puts in parametric equations of the surface, and that's way beyond the scope of understanding for middle and high school students. I get that, most of them, right? But the thing is, they don't need to know that. That doesn't matter. What matters is that they're telling GeoGebra, hey, you know what? I want you to take the surface found by rotating that function, that graph, a certain number of degrees, or in this case, radians, about the x-axis there. And we have a solid of revolution. A surface, I should say, of revolution. And now, here's the fun part. We're going to explore this in augmented reality now. All right? I'm going to readjust it, make it a little bit bigger so it fits entirely on my screen here. Okay? And now, I'm going to, before I do that, I'm actually going to change the color of it so it's kind of a brighter yellow in the background there. Maybe I'll do this, something like that. All right? And now, you'll notice that if you installed AR Core by Google on your non-iOS device, you should see a little AR button right here. Okay, what you want to do is tap on that now. Okay, and I'll do that right now. And so now, allow 3D grapher, you say allow, sure. Access photo, yeah, it's fine. And so now you see around me here. Oh, by the way, say hi to Mallory and Sarah. They're monitoring the comments for me. Thank you. All right, so now, ooh, look at that on the floor right there. You see all that? That's a great sign. Or you can see now what that is that means now my device is now looking to place the object here. So I'm going to tap. I could tap on the square, off the square, doesn't matter. Just tap it, and you'll see it come up right there. So there it is. I can go inside it. I can go around it. I can see it right on my Android or right on my Samsung tablet. Okay? Any device that has AR Core by Google installed on it, combined with GeoGebra 3D Graphing Calculator, the app we're in, means you could do just that. Okay, now, I want to show you something here. Now here's where, now it's sure you could really make it fun for students. Okay, so let's do this. Thank you, I'll just put it right there. Thanks so much. All right, so here we have a cone, right? And this cone here, let me just get it. This is actually built to scale. This cone has a height of 5 4/10 inches, and the radius is 1 3/8 inches. And so I would now ask my students, say, hey, you know what? Does this right circular cone here, is this a good model for it, you think, what I have up there? I put it right there. What do you think? And the kids will be like, no, no, no. And I work with teachers too. It's like, they tell me, no, it's not a good model. But now I'm going to ask you, I'm going to ask you viewers now, feel free to comment away. The Mallory and Sarah are watching the comments here. But what do I have to do to that function f in order to make it best fit this cone here? Again, I'll leave this right here. Okay. The height of this cone is 5 4/10 inches, and the radius of this cone is 1 3/8 inches. So what do I need to do to my function here in order to make this cone, this yellow cone that you see right here, like a like literally perfect model of this white cone right here? Any ideas? No? Okay. That's right. There's like a 10-second delay too, but we'll just wait another couple seconds. But that's okay. It's 9 o'clock at night. We're tired. 8:76 in the US. I get it. But here, let's just take a look at something here. You got on my screen. I want to just share something with you here. I'm going to, do we have a comment there? Let's see. Let me go to Google Chrome. I want to show you this. All right. Take a look at this here. Let me see if I can move this around. Now, here's the radius, right? Let's look at a cross section here. I mean, the line is really that slant right there, right? Here's the radius. Isn't that the radius of the cone? And here's the height. How does the radius and the height compare? How does it relate to this equation right here? What do I have to do? Any comments? That's okay. That's all right. No, it's all right. No, you're not obligated to type anything. But actually, if you think about it, isn't the slope of that invisible segment there really the radius to the height ratio? So now watch what happens here. Now kids working cooperatively should be talking with themselves and saying, hey, how can we just model this? But you know what? Let's try to make the rise to run ratio 1 3/8 all divided by, what is that? 5 4/10. And also, I think I should perhaps, since the height of that cone goes all the way out, according to my screen there, right? Shouldn't I also make the height of that cone perhaps 5 4/10, maybe? See what I'm saying? So let's see what this does. Ooh. X goes now from 0 to 5 4/10, and the slope of that cross section right there, again, let me see right here, right? The slope of that line that I can look at right over that segment, the slope there, right? If I go right here for a second, that rise is 1 3/8, and that run is 5 4/10. So now I form the surface. My kids form the surface, and this allows kids to do what they could never ever do before, is to actively model, number one, but now we can test the model accurately right here. Watch this. All right. If students build it fairly accurately to scale, you will see something like this happen. There you go. Look at that. See how it wants to almost hug on it. It wants to latch itself to it. It's crazy, right? It's pretty amazing. Let's just try one more example right here. Okay, and here is a shorter and fatter cone. Let me just get this stuff over here. Sorry about that. Right over here. Okay, this cone has a height of 2 3/10 inches and a radius of what, 3 1/4? Looks like. So now, what would I do to change? What do I need to do to change? I think most of you can see what we need to do here. We need to alter the end value here, right? 5 4/10 here to what, 2 3/10? Because the height is 2 3/10, and then the slope here is going to be now what, R to H? That's what, 3 1/4. 3 1/4. Oops, not 325. 3 1/4 divided by no, I'm sorry. Yeah, divided by 2 3/10. Enter. Oh, definitely shorter and wider. So now let's put this to the test and see. Okay. And actually, let's make it full screen. I could actually hit the down arrow there to see everything. And let's make it really smacked up in our faces here. Let's see. Get this cone out. Try it. And yeah, baby. Voila. Again, we're not shooting a rocket to the moon. I get it. But you know what? Talk about synthesis, creation, and stuff like that, and the whole DOK. This is like DOK 8 on steroids or something. Like, this isn't, for kids to be able to create their own mathematical models, I think, is so powerful that if kids can create like this, then the what, how to's like obviously tend to become second nature. Now, not only that, but we stuck with linear functions here, right? But let's just play around with this a little bit now that we're still in. We're going to go to the iPad in a few minutes, I promise. Now, this is one of my wife's lovely pottery pieces right here. She made this bowl in her advanced ceramics class many years ago, and so now I want to find a function that best models this. So let me actually just hide this for a second so you can see that. But if I can poll everybody here, if I actually held this bowl so that the center of that circle is right at 0, 0, 0, I know it's hard to see there, but looking down on the XY plane, right? How would you, let me actually show the plane again so it might be easier to see. That gray plane there. There we go. So it's kind of intersecting there. So there's the XY plane we often study, right? But how would you describe the intersection of that gray plane and the bowl? What does it look like? It's like a curve, right? But what kind, does it remind you of a certain kind of function that kind of curves up like that? Any kind of curve? All right. No? Square, yeah, there you go. Square root, exactly. Well, I messed around with this. I actually did a regression, but just to save time, just to show you here, when you have kids take a ruler, actually, or maybe even on their phones, they can measure electronically right now. I think they should be doing both. But hang on a sec here. One sec. Let's actually hide the plane first. Get rid of that. Show plane. And now we'll do the equation I put in here. So right here, hang on a second. I think I did something like, where was that? No, there it is, 0 to 5. We will model this bowl, 0 to 5. And then actually, I think the function I used was 1 and 9/10. Whoop, 1 and 9/10. If I could type here, square root of x. Square root of x. Get rid of that other x there. Plus 1. And let's see what this looks like now. All right, so let's show it now. Whoop. Hang on a second, and surface. There we go. Whoa, coming at you. Well, you know what I need to do? I need to go back to 3D for a second, hit the 3D button. Actually, because see, it's actually a static image you get in GeoGebra AR for now. I mean, the goal, I think the team is working on developing a version of it where you can actually move points in the space around you. I mean, it's so amazing what it does right now, but I could form it right here, right? The bowl, right? So there it is. And so now what I'm going to do is literally, no, I'm chopping some of it off. Let me zoom back just a little bit. There we go. And now we'll hit AR, aim it at the floor. Beautiful. And then there's the bowl. And now let's check it out. Let's actually model. See, this is the part. This is like the part, like the euphoric high you can get, your students can get when they're like, oh my goodness, like sort of like that. They come here, and now we'll put it right behind. And what do you think? Right? Real world, real life mathematical modeling. Listen, I'm not knocking those conics projects we do in 2D, like, make a smiley face, use one of each conic section, and the Batman equations we see. You know what? Those projects are needed. They're necessary. We should be doing that. But you know what? Many of our students who work in 2D can definitely also do so in 3D. They really, really can. And and GeoGebra Augmented Reality provides those students a way to do just that. How about this? Let's go back to middle school geometry for a second, right? Kids discover, oh my gosh, I get a cone. But what if I just did a constant function? See how this is the function y equals 1? Right here, this is the function y equals 1 from 0 to 5. If I spin a horizontal line about another, if the line is, let me show the function there. There's the black graph right there, right? If that line is parallel to the axis of rotation, students struggle to see the cylinder. I've seen teachers bend a piece of paper around it to say, but you know what? Let the kids build it themselves. They so can do that. And some teachers be like, oh, Tim, you don't understand. Like my kids, like I got to teach. And I tell those same teachers, I'm like, look, you know what? I'm not trying to argue with you, but those are the same kids that figure out how to circumvent the IT department and get on websites that the school blocks. You know what I mean? And if those kids have the smarts to do that, these kids also have the smarts to type in 3 lines of code to get a surface of revolution. Just saying, right? And yes, we can. You want to go through the tunnel? We could totally go through the tunnel. Let me take my headphones out for a second. Let's travel. First virtually through our tunnel, our little straw here. We may, oh, hang on, a little out of control here, but we can go through. Hopefully the device doesn't get too far away, and here we go. All right, go back through, and yeah, again, kids can have so much fun with this. Again, before I get to the iPad, I know it's about a half hour. This will do a half hour on the iPad, but before I get to the iPad, I want to give you Algebra 2 teachers and pre-calculus teachers an idea, and even calculus too. Okay, so in terms of modeling in 3D, I want to take a function. You know, just because like, oh, it's not part of it's not in our curriculum, Tim. I'm like, yeah, so what? You know what? I used to teach stuff in the curriculum all the time. No one ever I never got in trouble for it. But here's the thing: if you actually, let's go from 0 to 4, right? And let's rotate the sine function. See that sine wave right there? And let's actually spin it. What does it look like? I don't know. What do you think? What do you think it looks like? A fishy, right? It's a little fish. And we can go now here. So I always like to. So I like to ask teachers. It's like, why don't you ask your students this question? Now there's a fish, right? Kind of right there. You can model it. We can jump inside of it. And by the way, notice here a common theme. This same process that we're doing by spinning a curve about a function about the x-axis. This same task can be done by middle school geometry students, right? And AP Calculus students, but for two different reasons. The AP Calc students want to see what the solid of revolution looks like, just see it better. But the kids in middle school and high school geometry are doing this to actually describe what the surface of revolution actually is. Like parallel line makes a cylinder, slanted, a cone, or frustum of a cone. You see what I'm saying? So it's the same activity, but for two different purposes. But what's the common thing among both of them? Student-centeredness. Active learning, engaging learning. Students are physically and mathematically modeling the world around them. It's just unbelievable. Let's actually, this yellow is I'm kind of getting tired of this yellow here. Let's make it kind of let's spice it up a little bit, make it a little blue. That should have been that. That looks better, don't you think? I think that's better. Yeah, totally. Thank you. She's nodding. All right, good. So now we can actually, we can go get eaten. But now, here, my next question is, what should I do to put a mouth on this fish? Ask your students that question. What can I do to actually open a mouth here? And I'm willing to tell you that even if those kids, even the kids that somehow appear to have an IQ of a single digit, they really don't, and you know that, obviously, right? But those kids can tell you, you know what? Just make the 0 like 1 or 2. Now, we talk about domain restrictions, but let's be honest, high school math and middle school math teachers, what students really give a crap about restricting the domain of a function? It's not the most exciting thing we talk about, right? But you know what? Maybe for calc kids solving an optimization problem, they got to find the boundary values of something. But here, you know what? By actually making this, I think if I make it like say 2/10, I can open this mouth. I mean, to me, that's like intrinsically motivating. I mean, you get what I'm saying? But I can disguise the limit here to what I can do and create. I actually saw a tweet by a gentleman named a colleague of mine named John Golden. He's on Twitter. If you don't follow him. Follow him. John Golden has an amazing set of ideas. I love seeing what he tweets. But John once tweeted something about having his pre-service. He's from Michigan. I forgot what university he's a professor at. But he tweeted something and he said, you know what? He said, I gave my pre-service teachers projects where they had to take all the pieces of a chessboard and they actually authored, say, several functions up here, right? And they did this very thing right here. They took they did surface function, surface function, x-axis, surface function, x-axis, right? And honestly, he actually tweeted a picture of one of the students like did a queen or a king, and man, it looked pretty good. But now imagine giving your students, say, an open-ended task like that, performance-based assessment like that, but then you add this augmented reality component to it, and then the students can actually virtually test those models by just putting something right behind here. You see what I mean? And see how well it fits. Again, not a perfectly perfect test, but man, it's if you build it accurately, it will just lock on. It really will. And I could just even give the kids another question. It's like, hey, you know what? What can I do to get 2 kissing fish here? I mean, you can sort of see the symmetry here about the plane containing the y-axis here, or the YZ plane. But right here, what if I went from -4 to 4, right? And see how this kind of makes 2 kissing fish, right? again, the sky's the limit to what you can have kids create here. And for AP Calc teachers, again, I'm going to get to iPad, and I know I'm half past. I'm going to get to iPad in just a couple minutes. But right here, right, what if I were to do, in this app, you can actually duplicate commands. So if I go here, the 3 dots, I can actually duplicate it. And just so I have to type all that stuff out again. But I want to do, let's just say I want to make a cylinder. I'll just say y equals 3, right? So there it is right there. And then I'm going to rotate that thing about the x-axis as well. So go to settings here. Whoops, my bad. Touched the wrong thing. We go here, duplicate it. So I made 2 of those fish now, but I want to take the surface and rotate G about that. See? Now, AP Calculus teachers, when your students have to find the volume of the solid, formed by rotating the area in between the graphs of 2 curves, you get what I'm saying? I mean, really, it's not really shown. It's really the space inside this thing that you're really calculating the volume of. But definitely, man, I mean, when I was in college, man, how much better I would have done if I could have seen a cross section, like literally like kissing me right in the face right there. It's just unbelievable. It's out of this world. I love this app so much, and its implications for teaching and learning. It's absolutely great. Oh, and one thing I forgot to show you here. I'm going to just delete this for a second. Check this out. Did you know you can actually take this and rotate about the y-axis too? That's right. Just change x-axis here to y-axis. If you don't believe me, let me just go back from 0 to 4 again. Watch this. Let me hide G, the curve G there. If all I do is change x-axis to y-axis, look at there. Oh, yeah, baby. Right? In fact, you can actually rotate about any line diagonally in the 3 space. That's how powerful GeoGebra's 3D capabilities are. And it's a free app, and it's just out of this world. It is literally the world's best. It is the best of the best. And with respect to kids modeling and building in high school and middle school, they can so do it. Okay, so that's a little tour on in this case, I have the Acer Chrome Tablet 10. Thank you. Right here. It's available. I know I got it on Amazon, but I'm not sure if it's in stores yet. But a lot of school districts are going this route, or maybe not a lot. I shouldn't say a lot, but I think it's actually if you're a high school or ed tech administrator perhaps, and you're considering devices, that may be a device you want to consider because there's no keyboard there. It's like, look, it's a tablet. Yeah, it's a little pricier than the ones with keyboards, but here's the thing. When it comes back at the end of the year, when kids hand in their devices, you're not going to have the issues with, busted keyboards and so much cracked screens. And if mom and dad want to buy a virtual Bluetooth keyboard for 30 bucks, let them, just a thought. So anyway, let's actually, were there any questions? I'm just going to switch over to the iPad for now. Okay, that's cool. It's all right. Maybe there's something I didn't think. I don't know. But anyhow, let's see what we can do here. Go back to Air Server. Just give me 1 second. Let me stop sharing. Hello again. Just gotta switch gears here. Un momento. There. Go. Switching up. Show the code. Oh, so I can connect. We're on. Good. All right, so let me share again, and we shall rock and roll in the iOS world. All right, so Hangouts and share. Sure. All right, here we go. Screen sharing again. And over here, we have the iPad. Here's an iPad Pro. All right. But so interestingly enough, augmented reality here, okay, is that app that you see right there in the corner. All right. And so I'm going to hit the AR button now. It's right there. Now, right now, in terms of functionality, okay, you cannot do as much right now in the iOS app as you can do on the non-iOS app. But I assure you that is going to change. Okay, it's not a matter of if and when, because right now the 3D graphic, hello there, what should we name them? I don't know. Because right now the 3D graphing calculator app is only available for non-iOS devices at the moment. But for iOS, it's an augmented reality app. The graphics are amazing, but right now you can only enter in 2 surface equations, where Z is explicitly written in terms of X and or Y. So right here, and teachers like, Tim, what do you mean Z? I'll explain. Well, example here, this fish was created by rotating a cosine wave, basically 360 degrees about the x-axis. We can jump in the eye, kind of, if Tim Burton taught math, maybe he would be proud. I don't know. But right here, kind of going in and out, we can actually see, we can animate stuff. We can have them swim away slowly and surely, kind of off into the distance. Oh, where'd you go? There you go. All right. But let's actually get rid of this. And let's just start with the very basic. Let's talk about the conic sections. All right. Because that's a big thing we talk about in many Algebra 2 and pre-calc courses. So, when you have kids play on this, you say, well, right now, you just tell kids the output is not y anymore. The output is z, right? Right there, the z-axis there. In this particular app, x goes from -5 to 5, right? Y goes from -5 to 5 here, the green. And z goes from -5 to 5, all right? So instead of typing y as a function of x, have your students type in z as a function of x. So for example, z equals 0. Oh. But wait, doesn't that look like y equals 0 if I just kind of hold it like this way? You see what I mean? And what if I make it z equals 1? You see, it's literally, it's so analogous to what you're already doing in the two-dimensional coordinate plane. So why not take time to have kids model the real world in 3D? All right, you can do that. And so now let's go back to z. Let's make it z equals. Now let's talk about this. Now students would not necessarily know that this surface is the equation of a cone. But so what if they don't know that? Give it to them. Let them play around. Let them build. Now, if I were to ask teachers, hey, how would I flip that cone upside down? What would most of you say? Oh, Tim, make it negative. Yeah, put a negative there. You see, all your function transformations that are going on are still happening here. Okay, and what if I wanted to shift it right 2 units along the x-axis? Oh, that's just, you got to subtract 2 from the input variable x. Okay, so yes, I'll make that x minus 2, right? You see what I mean? The same transformations. Now, why is it chopping out part of it? Because remember, this app only goes to -5. Okay, I'm sorry, to 5 right there. All right. So now, if I want to really do something, I have to kind of center it to whatever. But if I add to it, right, then it'll shift it left 2 units. The same transformations you do in 2D, also hold in 3D. Oh, and what if I want to actually add or subtract from y? Can I do that? Heck yeah, you can. What if I want to go up, say, y minus 3? Where's that going to get moved? Well, that's going to be moved it's going to be moved 2 to the left, and then 3 here, right? And you can actually jump in. You see, have kids virtually build and explore. Okay. Now, what I love about even though this app cannot do as much as the graphing calculator app that we have in on the non-iOS, again, 3D graphing calculator is coming for iPhone and iPad. It is. GeoGebra is working on it. Again, it's not if, it's when. I believe it'll be this year, but again, don't quote me on it. All right, but I know that they're working very diligently on it. But right here, again, I could do practically anything. But let's actually just put that cone back in again. Let's actually explore the conic sections again really quickly. So we need a cone, a right circular cone here. All right, we'll flip it up there, and let's take z equals, let's say 3, or maybe 4. Look how clear that is. I love it. So now, sorry, let's actually hold it up there. All right, say hello. Aha, yeah, on camera. So right here, right? So you kind of go there, and we can actually go in. But what would you do? What would the cross section of that cone in plane be? When that plane is actually perpendicular to the axis of the cone, right, coming up right there, that plane is perpendicular to it. What does the cross section look like? Students can jump out of the seat and say, "Oh, it's a circle." Yeah, we can even go inside it and explore it literally from a 360 degrees. Okay. Now, what about what if I were to do this? Z equals x plus 1. That's like y equals x plus 1, right? Let me just hide this for a second. Isn't that like the line y equals x plus 1? But that line is not a line now. It's actually a plane. If that z-axis were y, what would you tell me the slope is? Wouldn't you say 1, right? And so now the slant of this cone here, the slope here, I mean, like, it's kind of hard to describe, but all the way around from like here on all the way down, right? The ratio of like delta z to delta x or whatever, delta z to delta, that's also 1. Okay, so what we have here is a plane that is actually parallel to, that purple plane is parallel to the slant axis of the cone, literally right here, right? And whenever you have a plane slant parallel to the slant axis, you actually get a conic section that is called a, starts with a P. Yep, parabola. That is definitely a parabola right there. Even if I did z equals x plus 2, right? That's still parabolic there. Now to make it elliptical, we could just mess around, right? Let me move it down so we can see the whole thing. There's your ellipse, right? Kind of right there. But again, I just love the feel of this. It's just like you can actually explore it, jump into it, dive in it. It's amazing, all right? And then finally, we could do a hyperbola, one branch of a hyperbola at least, like that. Okay, you know, hyperbolas tend to have that sharp curviness right there on this side and even the other. But the graphics here are pretty amazing. All right, they are also amazing on the Acer Chromebook tablet. It's just that the connection I had was very pixelated. So now, let's actually talk about how we could use this, for example, right? Let's actually quickly, we're going to actually build something that's a very common candy in just a minute. But before we do that, I want to go back and visit this cone. And you're like, well, Tim, hold on a second. Problem. You see in the other app, I was able to just simply do the function y in terms of x, and then you know, kind of have it just be what, you know, 360 about the x-axis. It was three. How am I going to do that with z? Well, that's a good question, but you do have a hint. I did tell my students I have this, right? Now the question is, what do I do? And that's where students start to, you know, put their heads together, working in groups, you know, collaborating and thinking, okay, well, you know what? Again, the same transformations that you study in 2D also hold true in 3D, right? So let's stop and think about this here. Maybe I'm jumping the gun too fast with two variables. So I realize now I probably should have did another example first, but that's okay. We're on this train of thinking here. But right here, all right, I mean, it at least has to open upside down, right? Because that cone is upside down. This one's right side up. So how do we open it upside down? We put a negative there, right? Now, here's the other key thing. The height is 5 4/10 inches. So this guy's got to get what? Bump it up, right? So think about math teachers. What do? We want to move a function up. Well, we just add to the output, right? Plus 5 4/10. We're getting there. And let's see. It's kind of, but nah, gosh, Tim, it's like that's way too wide. It's got to be much. Ooh, see, it wants to fit. You see it? See how I'm moving right there? It's crazy, all right? But now what do we do? Well, now we have to adjust. I can't really use the words just to save time here. I can't really use the word slope. But what I can say is, how about we take basically we have to stretch this thing out like a vertical stretch. And I'm not going to go to the y right now, but that stretch is actually going to be the ratio of the height to the radius. That h to r ratio is actually, if you want to think of it as quote slope unquote, that 5 4/10 divided by 1 3/8, right? Getting better, right? But now we still have a problem because you see from the red axis up is 5 4/10. This extra stuff has got to be gone, and the way to get rid of it is actually to put a domain restriction on it. And when I say, oh, see, I even grabbed the wrong code. That's funny. Now the domain of a function in 3 space is the set of all points in the coordinate plane x, y. So if I restrict it to x basically here, x squared plus y squared, right? Think that if I go inside here for a second, right? What's the distance from here? Try to be gentle here. It's like to the edge is like 1 3/8, right? Is less than or equal to 1 3/8 squared. I think that's it. There we go. Right? Isn't that the equation of a circle? See, for all these points right up here on the tippity top, right up the top here, like all the points on the surface satisfy that constraint that I just typed after the comma. See what I mean? And watch this. See if I get straight on here. There we go. Right? And so then you could have, and again, kids could be recording the screencasts. So again, this is definitely a higher level thinking task to them. There's nothing they can ask Alexa or Siri or whatever, you know? All right. So there you go. All right. That's how we can model in 3D. But then we could also do for the other one. But let's switch gears here. Let's still stay in Algebra 2. Let's talk about a simple function we studied in Algebra 2. All right. Or actually, no, even Algebra 1 for crying out loud. All right. Z equals X is like Y equals X, isn't it? Yeah. What about Z equals X squared? Predict what that's going to look like. Oh, well, you get an infinitely long parabolic sheet, right, that we can kind of slide on through and slide all the way back, right? Kind of like that. And how do we flip it upside down? We can flip it upside down, make a tunnel, right? Students can work with the most basic of equations here. Notice how there's only two variables right here. Let them work with only two variables first, but the dependent variable now has to be z. So let's do it plus 5, right? And then over here I can go z equals 0. And then now I ask kids, well, how can I actually shave off this extra, stuff here? I don't like that. I just want it to be like the arch and the road. What can I do? Then have kids think, oh, Mr. B, it's just you got to find the x-intercepts there. And I say, yeah, what are they? Oh, negative 2 points. No, come on. Oh, it's square root of 5. So we could just quickly do it by absolute x is less than root 5, right? Looky there, getting better. And z equals 0. Again, another way to type that is just simply, as you know, is negative root 5 less than, whoop, my bad, less than equal to x, right? Less than equal to 5. Oh, I forgot root 5. My bad. There we go. And see? Again, a basic construction, but again, see how we only have two variables still. We're working, again, keep this in mind, we're working in 3 dimensions right now, but we only have 2 variables. Instead of y and x, we have z and x. So tell me why many students can't do this? I can't think of a reason. They should be. Again, my opinion only, but hey, we live in a 3D world. Let's pretend like it is the 3D world we live in. So there we go. Now, let's actually mess around here for a second. I want to show you something here on the Chrome here. Check this out for. Nope, hang on. Check this out for a second. All right. Notice here. This, I mean, like we often ask students, hey, find the center and radius of this circle right here, right? And we expect the kids to say, oh, well, it's the center is 2, 0, and the radius is 2. And very good, you're right. Now, we could type that on the Acer Google Chrome Tab 10 or a non-iOS device and get it. But right now, again, for iOS, we're limited, but that's okay. That's going to change. But still, when kids solve for y here, don't they get the upper root and the lower root right here? That's like really a cross section there, right? So if I go here, for example, let's go back into AR right there, and I'll do literally just what I showed you right there. Let me just put this to the side. All right, and hang on a second. Let me just move this over. There we go. Try to get it. Okay, so I'm going to type those equations that you see right there. I'm going to type those right in here for where the plus signs are. So z equals the square root of, what was it, 4 minus x minus 2 quantity squared, right? But see how that looks just like what you see on it looks like just what you see on there? But what's the difference is that it's simply, it's just 3-dimensional. It doesn't matter what y is. It just extends out indefinitely. So now let's put the negative branch down there. See, your students can so do this. They so can. 4 minus x minus 2 quantity squared. All right, and there it is. And one little trick that I've also learned is then I give kids a challenge. How can you make 2 tubes with only 2 equations? There's 1 tube. How can you make 2 of them? It's like, ooh, yeah. How do you make 2 tubes? Well, think about it. Is there a type of function you could type that has 2 outputs for every input? Well, again, that's kind of a contradictory question because every function has to have only 1 output. But how about if I input 2 items, it comes out to the same output, perhaps? That's probably a better way. But check it out, just to save time. If I change this x here to an absolute value of x, you get 2. Right? Because technically x could be, in this case, x could be the negative or the positive and all of that, right? And over here, and so now I can just simply go, hey, absolute value of x. And now I have 2 tunnels. Like it looks like a pair of binoculars, right? That I can go and see through and say, hey, you still paying attention? All right, sorry, whatever. But now I can go through, do whatever. But now I ask kids the challenge and say, let's progressively work our way up here. How can I tilt these things? I want to tilt them this way. Oh, Tim, you're killing me, man. Or this way, I don't know. But wait, what that variable going in that green direction is what? Y? Oh gosh, what if I just added y? What if I just added y? Holy moly, you kidding me? Or maybe we should just do a half y. But see, now we get kids who are capable, not every kid, but we get kids who are capable going in those directions. And see, now we can make a slide. Whoop, kind of like that. Sitting there. Or how could I make a wavy slide? What could I make a wavy slide? What kind of functions are wavy? Oh, trig functions. Yeah, let's make it cosine y. Yeah, baby, look at that. And we can go 5 here, and then let's put a, again, we're studying z with respect to y now. It's like we're still working with 2 variables, even though there's 3 here, but we have really 2 main directions we're working with, parallel to the y-axis and parallel to the x-axis. So now, and I could even adjust the amplitude of that thing. I can make it like, let's make it, well, hang on a second. Let's make it 2 cosine y and 2 cosine y here. Holy moly, look at that. And go nuts, right? And go in. Let's see if I can do this. Go in without bonking my head in the side there, right? There, and then, right? Yeah, whatever. But you get what I'm saying. So, again, let's see, that's what I love about this app too, is that it lets mathematics become a form of art for students. Real world, real life 3D art. Again, mathematics, yeah, it's a science, but it also could be an art. Let kids create. Okay, kids, that could be an intrinsic motivator for so many of them, even in your Algebra 2 classes where we're studying functions that seem so typically boring, like absolute value functions. But hey, who would have knew that absolute value can produce 2 of the same thing? It's pretty cool. I wanna actually switch gears here. We'll end with this. All right. Now, we get up here. Let me see here. So we get there. Every math teacher's favorite candy, right? Try to put this aside here. My bad. Here we go. We talk to the iPad, right? Why not? Why do math teachers love Toblerone so much? Why? Well, you can answer, but isn't that the only thing in life that we could think of that's actually a triangular prism? It makes math teachers excited, right? Now, the base here is an equilateral triangle, okay? And we have 3 lateral faces, obviously. Here's the height. So now, here's my question for you. That plane, if we just rest it here, right? Let's say rest it here. I think the equation of the bottom plane is fairly easy, right? What was the equation of a plane that was just pure horizontal? Was like what? Think of the equation of a horizontal line. Y equals a number. Well, in this case, wouldn't it be z equals a number, right? So let's actually do that here. And let me get out of the camera. We'll open up AR. And let's type it in. Z equals 0. Boom. Here we go. All right. And now, here's the challenge. Here's the challenge, right? I will take questions. Do we have any questions? Yeah? No? No questions? That's okay. People just watching. That's good. So now, how could we check out this part right here? What does this part look like right here? I'll give you a hint. That pink surface right here, this pink part right here, right? What kind of a function looks like that V? Come on, I know you're all shouting it now. Yes, I know it's late. I get it, but isn't that an absolute value function? So we can model a Toblerone, which is a simple absolute value function and a horizontal plane. Yes, your kids can do it. And let's see. So let's actually type in z equals. Let me make the bottom z equals. I'll make the purple one z equals 0 because I want to see the blue on top. So there it is, right? And now let's do z equals absolute x. Now, I work with teachers a lot, and I ask them. I ask teachers, I want you to help me build this Toblerone. Well, what's the first thing that's got to change? Oh, you got to flip the v upside down. So what do I do? Oh, you got to put a negative in front of it. Okay. All right. So now we're building. We're getting there. Oh, but then you got to bump it up a little bit. But how much do we bump it up? And that's a great question. I'll give you a hint. Even your geometry students, we can do this in geometry as well too. Yes, we can. Algebra 1 geometry. Let's see. Here's a hint. You see my screen right there. That blue cross, that's the Toblerone candy literally right here. So let me ignore the stuff. Let's just look at the Toblerone, right? That blue triangle on the right is really this triangle right here on the left. What is the delta z to delta x ratio? Remember, that's an equilateral triangle there. So think about it. Your students should be thinking about it, talking about it with each other. What is it? Well, it's we have 60, 60, 60, right? Draw the line of symmetry down the middle, draw the altitude. It cuts into 2 what kind of triangles? 30, 60, 90, right? And then what's the ratio of delta z to delta x? You know, those teachers that love that SAT chart. Oh, no, it's root 3. Z isn't delta z really root 3 times the length of root x, right? I'm sorry, delta x and not root x, delta z to delta x, isn't it really the absolute value, I'm sorry, of delta z to delta x is really root 3. But there's got to be a negative in front of it, right? So let's actually put a root 3 in front of it. Square root 3. Again, root 3, this is 1, right? We're going to make this be 1. And we're going to let this be root 3. Okay? So negative root 3x. But then, oh wait, what do we have to make this here? This distance was what? If we call this 1, we call this root 3, right? Plus root 3. And I guarantee you that cross section is a perfect equilateral triangle. But wait, where does it hit the x-axis? I can see it so clearly. Oh my gosh, at 1 and at -1. So now we can go happy with domain restrictions here, right? So, whoop, my bad. So -1 less than equal to x less than equal to 1 for the blue. Do the same for the purple, or I'll just quick and do it this way, right? And there, ladies and gentlemen, is the Toblerone candy. But wait, there's one more dimension. We have to talk about the length of this and the length of that. What was the value?
21 centimeters.
So this was 21 centimeters long. The height was 21 centimeters. And what was this edge of the equilateral here? 3.5. So how many of those go in there? So it's how many 3.5s fit in the 21? The 6? So let's just go from, let's cut it in half. So just save time from -3 to 3. See, no, -3 less than equal to y less than equal to 3. Right? We'll just say absolute value of y. Or what was it? Yeah, that's right. But let me see. Yeah. Oh, you know what? Because I thought that it was, because we're running out of time here. Let's just do it. We'll just do it. We'll just keep it like that for now. That'd be a lot easier. But now, see, kids will build that. Let's do the ultimate test. I'll hide this, superimpose it. At least we'll test the cross section piece, right? There we go. Makes me feel better. And then here we go. In fact, let's even put that on right there. Kind of do that and hold it. Whoop. And there we go. Actually, look it up from a bird's eye view. Let's see. Yeah. All right. So yeah, but that cross section is definitely equilateral. Maybe if I try to hold it in here. I don't know. It could be a little bit of it wants to kind of, yeah. There you go. All right. GeoGebra Augmented Reality. So again, the possibilities here are absolutely endless here. I did have more to show you, but I know that we're almost out of time here. The hour's almost up. Let me just go back here to the screen. Yeah, but so yeah, no, that's those are just some examples with respect to getting started. Have students build, let them play. I mean, like it's active hands-on discovery-based learning is the best form of learning in any situation except for two things. All right, you don't want kids doing hands-on learning when it comes to touching a hot stove or sex ed, and their theory is good enough, right? But anything else, you know what I can think of, it's like especially mathematics. If they're going to learn about triangles, let them cut out a triangle, let them build, let them play, all right? Let them explore, right? Learning mathematics is always a journey. It's not a destination, all right? So, but yeah, I hope this webinar has been informative. I hope it's helped you, maybe given you some ideas with respect to your middle, high school classrooms, and even, post-secondary as well. Any questions in the chat at all? Nada? No?
No, just jokes.
Jokes?
Yeah.
A lot of jokes?
Chunky is a truncated square pyramid.
Truncated square?
The candy.
Truncated square. Oh.
Yeah, the candy.
Oh, the truncated square pyramid. Oh. Well, I think because this is equilateral triangle if I put two of them together, but I'm not seeing a pyramid. Well, this is technically a prism. The prism has to have two congruent and parallel bases. But if you could explain in the comments below, that's I'd love to read. I'd be happy to answer any questions or comments that come up. But yeah, so again, if you're interested in social media links, all the information you need about that is listed in the description below in the YouTube and below the YouTube webinar there for information. If you like what you see here, feel free to visit my website. I love working with schools, districts all over. www.brzmath.com. You can find me on Facebook, Twitter a lot, Instagram. The social media links are there. So hour's up. Thank you so much for watching, and thank you for the feedback, the encouragement, the emails I've received and stuff. So I wish you and your students the very best on your journey of learning mathematics. Thank you.